Hi, welcome to RSJ Technical's Ask the Expert YouTube channel. Today we're going to talk about stoichiometric analysis for representing glass, ceramics, and enamels in IMDS. There's some important terms and concepts to start out with. First, let's talk about UVCB materials. UVCB stands for unknown or variable composition, complex reaction products, or biological materials, which is why we obviously call them UVCBs, because that was a mouthful. These materials have different constituents, and some of them may be unknown. The composition can be variable or difficult to predict. So these are sort of unique materials in the world. The next term you need to understand is stoichiometry. This is the calculation of reactants and products in chemical reactions. Basically, whatever molecules you start out with, the reactants, you end up with the same amount of stuff in the products after the reaction has occurred. For instance, if you take a molecule of methane and 2 molecules of oxygen, they're going to react to form a molecule of carbon dioxide and 2 molecules of water. But when you look down below, that you'll see that on each side of the equation, you have 1 carbon, 4 hydrogens, and 4 oxygens. They've just been rearranged a bit, but all of them are accounted for. We're going to use, IMDS has added what it calls pseudo substances, glass without declarable substances, ceramic without, and enamel without declarable substances. And for this presentation, I'm going to use the word ceramic, and you'll know that I'm including glass and enamels in the word ceramic for purposes of this recording. So we've got to talk about scientific reality versus IMDS reality. They're close, but they're not the same. In scientific reality, we care about the rules of chemical reactions. That's how things work. And the substances as they exist in the UVCB are what we care about. But in IMDS reality, the main thing we're concerned with is regulatory compliance. We're needing to track the GADSL substances, and that's more important than the chemical reality of a material. So remember that IMDS reality and scientific reality are really different. We're going to go through the wormhole and enter on the side of scientific reality. We're coming out on the IMDS reality side. So from now on, we're in IMDS reality. So how do we get from scientific reality to IMDS reality? And why do we care? IMDS reality requires that substances on the GADSL must be revealed and trackable in IMDS so we can meet regulatory obligations. There are compounds which contain GADSL listed substances, but the compounds themselves are not on the GADSL. If we lump non-GADSL substances together into one of those pseudo substances, then we can lose sight of GADSL substances present in a material. So there's a compromise between scientific reality and regulatory needs. So when did this IMDS reality become a thing? Well, it happened in 2013, so it's been around a little while at this point. And you can find more on the IMDS information pages. Go to Help FAQ Materials and scroll down to the FAQ on how to declare glass and ceramics and enamels in IMDS, and there's a link to a PDF that'll tell you more. But let's talk about how you get there. There's 5 steps. We're going to get the molecular composition for each substance in the material, determine the percentage of each element in each substance. Then, molecule by molecule, we're going to determine the presence of each element, the percentage of each element in the entire material. Calculate the total of each element in the material, regardless of what molecule it came from, and then decide which substances we're going to lump into the pseudo substances and which substances we're going to continue to show because we're tracking GADSL substances. So, step 1. Get the molecular composition for each substance in your material. So here's a list. of the molecular composition. For instance, diboron trioxide is B2O3. A lot of times the formula will be listed in IMDS, but if it's not, you can go to the internet and Bing it or Google it or Yahoo it or search however you care. You will be able to find it. Next, you're going to determine the percentage that each substance represents, or each element represents in the substance. So you've got to find the atomic mass of each element and then do a little math. So, for instance, boron has an atomic mass of 10.811, and there are 2 borons in diboron trioxide. So you're going to have 10.811 times 2. And you're going to do the same for oxygen, and then you're going to figure out the percentage represented by oxygen and the percentage represented by boron by weight in diboron trioxide. You can set it up on a spreadsheet, which makes it a lot faster and easier, especially if you have to do this a lot. Next, you're going to determine the percentage that each element represents in the total material, molecule by molecule. So you're going to figure out the percentage by its range. If there's an X to Y range, you're going to have to figure out an X to Y percentage for each element in each molecule. And again, do those calculations on a spreadsheet. It's so much simpler. And if you have something that's measured as rest in IMDS, then of course there is no X and Y, there's just one number, or the X and the Y are the same, however you want to look at it. Next, you're going to calculate the total amount of each element in the material no matter where it came from. So add up all your oxygens, add up all your carbons, add up all your hydrogens. Now we had in our material some silica, vitreous, and some miscellaneous not to declare. These percentages are automatically going to end up in the pseudo substance because silica vitreous is essentially glass at its most basic level, and the miscellaneous not to declare there's nothing we can do with because we don't know what it actually is. So we're going to throw it in the pseudo substance. So here's step 4. We have grouped all the oxygens together, grouped all the lead together, grouped the titanium together, and figured out the total percentages here of each of them. Finally, we have to figure out which of these elemental substances is on the GADSL and which are not. If they're not on the GADSL, we can dump them into the pseudo substance. If they are on the GADSL, we want to list them separately. We can also choose to list additional non-GADSL substances that we may want to be able to track in the future. For instance, you may want to list your tin, tantalum, tungsten, and gold substances if they're present because they're conflict minerals. You may want to list things like neodymium or ruthenium or iridium because these are critical minerals and you want to know where to find them in your supply chain. So now I've done some more calculating. I've grouped everything together and I've decided of all the things that are there, I'm going to throw the oxygen into the ceramic without declarables. I'm going to throw the titanium in, the zinc, the silicon, silica vitreous, and I actually decided to keep the miscellaneous not to declare on its own because I really don't know what's in it. So it's better to know that I've got some miscellaneous not to declare. I may need to modify that in the future. I've also chosen to keep the neodymium and ruthenium even though they're not declarable because they are rare earths and they can be important in securing future supplies to know that you might have a potential critical mineral that you need to secure. So what have we learned? Well, the next time you enter a spelling bee, you will be able to spell stoichiometry and use it properly in a sentence. Stoichiometry is the basis for calculating basic substance percentages for ceramics in the International Material Data System. But even better, you'll be able to create appropriate representations of ceramics, glasses, and enamels in IMDS. Thank you very much for your time today, and I hope you'll join us again for the next installment of Ask the Expert.